Maths is the origin for all great man-made structures, even those we take for granted, like the geometry of the seating in this very auditorium. Mathematics is often seen as a puzzle or a mystery, but it's more of an incredible story to tell. It's not just about numbers on a page. It's a tale about human curiosity, ingenuity, discovery, and the profound impact of mathematical ideas and how it shapes our world today. Unlike most stories, this one starts over 25,000 years ago with the Ishango bone. It was discovered in Central Africa and looks rather unremarkable. It's a 10 centimeter long comb like object with a series of notches along its edges. But it's not just an artifact showing humanity's first flair for counting. This represents humanity's need, their inherent need to quantify the world around them, and led to the series of events where we quantify everything. And every quantitative system we use today, be that timekeeping, banking, or even the algorithms in our computers, come from this first spark. Next, we have a few clay tokens from Mesopotamia, which again look nothing out of the ordinary, but they are the original precursors to our monetary system. So in Mesopotamia and Sumeria, traders used these as different shapes or sizes representing different values, and this pretty much parallels the current monetary system. This is the origin of our financial structures, but not only this. These tokens laid the foundation for our written language. And here's how. Students, scribes, and teachers in ancient Mesopotamia found that they could take these tokens and print them onto wet clay tablets to form what you see at the bottom. And around 50 to 60 years after developing this, we had humanity's first ever written language, cuneiform. It's needless to say how important written language is, but I'll say it anyway. Written language is why humanity is as advanced and more advanced than any other species on Earth. It's allowed us to transmit knowledge, history, culture across spatial and temporal dimensions like no other animal. Here's another tablet called the Plimpton 322, and it has a few columns, and these are Pythagorean triples. And just a quick refresher, Pythagoras was a mathematician. He made an equation called the Pythagorean theorem, which states a squared plus b squared is c squared. And you have the Pythagorean triples, which are integers or whole numbers that satisfy this equation. But there's a bit of an issue with this, and it's that this dates back over a millennium before the birth of Pythagoras, leaving it as one of the most controversial mathematical artifacts of all time. But then again, that comes to show the timeless nature of mathematics. And in fact, this was used, the Pythagorean triples were used to ensure structural integrity of right angles in buildings and infrastructure. Here is the Rhind Papyrus. It's 2 meters long, and it's essentially the first mathematical textbook. It's a compilation of problems with multiplication, division, geometry, and fractions. And it was the first example we had of a mathematical textbook, and it shaped the pedagogies we even use today in our learning in the math classrooms. And particularly in ancient Egypt, with students being able to become computationally sound through the usage of such textbooks, we have been able to enjoy the most iconic Egyptian structure of all time, which are the pyramids of Giza, because each pyramid, the elevation of each pyramid corresponds to 3 constants, which are pi, phi, which is the golden ratio, and E, which is Euler's number. So this sound understanding of computational mathematics is really what allowed ancient Egyptian mathematicians to develop the intricacies of the pyramids, and is even what we've adopted in our current teaching methods. Now here is a copy of a page from Euclid's Elements. A few people might have heard of it. So Euclid was a mathematician, and geometry is actually a short form for Euclidean geometry. So he, over the course of his life, compiled all of his knowledge into 13 books, which he called his Elements, which were definitions, postulates, theorems, and proofs which he had developed. And this forms the basis of almost all of our understanding of Euclidean geometry, which is basically what we use in almost all spatial-based fields like engineering, architecture, design, and technology. So it's pretty important. One of the final ones is something, so we've talked about geometry as one of the main fields of math, but now there are also other fields, right? And this is called the Compendious Book of Calculations by Completing and Balancing, which doesn't sound familiar at first, but in Arabic, that shortens to al-Jabr, or algebra as we know now. So this provided a way to solve linear equations, quadratic equations, and finding the areas and volumes of various geometric shapes. But more than that, by laying the basis of algebra, you develop human problem solving, and with the advent of advanced problem solving, at the current day, we've been able to develop technologies like machine learning algorithms. We've been able to develop advanced cryptography, financial modeling, and most algorithms for computers. So this is what laid the basis for almost all of that. Here is the Dresden Codex from Mesoamerica. It's a manuscript from the Mayan civilization pertaining to their understanding of math and astronomy. It uses a base 20 numerical system. We use a base 10 system, which is known as the decimal system. And it contains almost all of the Mayan predictive astronomical analytics. So how to predict when an eclipse would happen or the movement of Venus. And what's cool is that even a few thousand years back, the Mayans used such advanced computations that we actually use the way which they used to find eclipses in the current forecasting system. Penultimately, we have the Liber Abaci, which in Latin is the Book of Calculation. It was developed by Leonardo Fibonacci, who was the son of a Venetian merchant. And he did three main things over the course of this book. First, he propagated for the use of the Hindu Arabic numerals, which are the numerals we use today. He also provided a sound way to calculate profit and interest, which is very relevant to our current lives, and how to determine prime numbers, or at least the elementary part of that. And that seems kind of abstract, but determining prime numbers because of their properties is very, very relevant to cryptography. And finally, something from his very namesake, he developed the Fibonacci sequence, which can be used to describe many, many, many natural and metaphysical processes, and could have its own TED Talk, to be honest. Finally, we have the Incan quipu. So it's strings adorned with small knots at irregular intervals, wherein positions and the colors of the knots determine the records. And in this case, records could be dates, could be times, it could be numbers. This was the first example of numerical organization, and it actually foreshadows current data management systems which we use in computers. So our journey through the tapestry of mathematical history has revealed a pretty interesting odyssey about human ingenuity, from the inscriptions on the Ishango bone to the meticulous knots and their intervals on the quipu. Mathematics is far more than just an abstract facade. It's the silent architect of almost everything we have today, be it our monetary systems, be it our written language, and much more. So, as we stand at this metaphorical crossroad of ancient wisdom and modern insight, let's take a moment to appreciate math for more than just a chore of calculation, but also a testament to human exploration. And when we find solace in solving geometric proofs which originally derived from Euclid's elements, or just marveling at the intricacies of Fibonacci sequences, remember that behind every theorem, ancient tablet, and meticulously tied quipu knot lies the indomitable spirit of human discovery. Thank you for embarking on this journey with me. I've enjoyed it, and I hope you have too.